Hemophilia has been seen in society from ancient Jewish laws to the disease's progression through the royal lineage up to modern diagnosis. The scientific understanding of this disease, however, has only been present in the last century. Hemophilia is an X-linked recessive disease categorized by diminished coagulation factors and impaired hemostasis. Let's break that down. Hemophilia impairs the body's natural ability to stop bleeding and creates greater risk of serious injury. Hemophilia is a hereditary disease marked by mutations on the X chromosome. Therefore, only males are usually affected. Healthy hemostasis, the reaction in our blood vessels after injury, goes through two main processes. Primary hemostasis constricts the blood flow to the injury while platelets form a plug over the damaged area. Secondary hemostasis involves the coagulation cascade, a series of proteins activating each other at the site of injury to eventually create a stable clot. Hemophilia directly affects the coagulation cascade due to missing protein factors. Hemophilia A is missing coagulation factor 8, and hemophilia B is missing coagulation factor 9. Hemophilia A is the most common form of the disease. The F8 gene is a protein-coding gene for factor 8. This gene is responsible for producing the protein, but in many hemophilia patients, the gene has mutated. For severe hemophilia A patients, the most common gene mutation is an intron 22 inversion. Following the pattern of many other genetic diseases, if the genes, then proteins, are different in form, they will not work as intended. In hemophilia A and B, the missing factors cause lifelong symptoms of prolonged bleeding. Science has worked endlessly to create therapies to combat hemophilia and extend the lifespan and quality of those affected. The most common treatment today is infusions of missing clotting factors. With the dawn of recombinant proteins, coagulation factors 8 and 9 are manufactured in the lab and used in treatments like the infusions. Gene therapy, a therapy currently in clinical trials, is a procedure where a healthy version of the F8 gene is inserted into the liver where the coagulation factors are primarily produced. After the procedure, the inserted gene will replace the mutated gene in producing the missing factors, hopefully a one-time fix. Gene editing is the future of genetic disease cures. CRISPR, a gene editing tool originally found as a bacterial immune system, can be adapted to edit specific genes that are linked to diseases. CRISPR-Cas9 is able to cut out the mutated genes and replace them with healthy versions when supplied with guide strands of RNA and the desired DNA. As the understanding of hemophilia and its molecular workings come to light and future therapies progress, the diagnosis becomes less of a grievance sentence for those with the disease.